So, good morning. Today we will look at a new topic, that is we are moving away from the fundamental quantum mechanics of electrons and certain types of potential constraints to the actual behavior of electrons in real solids. So, as we discussed towards the end of the yesterday's class, one of the common way of describing the electron potential inside a crystal is called the chronic penny model. Okay. So, you can talk about the atoms distributed in a lattice structure which forms the crystal in a one dimensional framework, and the interaction potential between the atoms can be represented like this, and therefore, the electrons moving within the crystal is actually constrained by this interaction potential. Okay. So, when we now look at therefore, a real crystal which is periodic in nature, we have to solve for the wave equation for the electron motion confined to this particular potential constraint. So, in the chronic penny model, this interaction potential is further simplified by using the rectangular potentials of this particular form. So, essentially you can think about these quantum wells of width a, okay, and these are separated by means of small barriers of width b. Okay. So, this is basically the simpler representation of the actual interaction potential. So, this particular potential is therefore periodic. The periodicity is a plus b. So, every a plus b this potential keeps repeating. So, for our solution, we will consider a coordinate system where we start the origin somewhere at the end of the potential barrier, okay, and we will have a coordinate system where we take the potential barrier width. So, this starts from minus b to 0 is essentially the potential barrier width, and from 0 to a is the quantum well width. Okay. So, this is one unit cell representation. So, I will just mark the unit cell here. So, this is going to be the unit cell or periodic potential inside crystal. So, we do not have to therefore look at all of these potentials together. We can take one periodic unit cell potential, and then we have to apply the periodicity boundary condition, right. So, the boundary condition here is it is periodic at x equal to minus b and x equal to a, and apart from that you also have to give the boundary condition at x equal to 0. Okay. So, this is where the transition happens from the confined electron within the potential well to the free electron which can cross this barrier of width b. Okay. So, let us say that the height of this quantum well, potential well, basically is u naught. Okay. So, that is also the height of the barrier. So, the potential distribution u of x therefore is given by u of x is given by 0 for x greater than 0 less than a, that is inside the well, right, and you have potential barrier constraint u naught for x greater than minus b less than 0. Okay. So, now we have to solve the Schrodinger's equation with this for this particular periodic potential with this kind of constraints. Okay. So, can you again write down the spatial form of the Schrodinger's equation. So, for this case again you have d square psi by dx square. Okay. So, then you also have the potential energy constraint in a generic case. So, so we will be solving this for put u naught for the case where x is greater than minus b and less than 0, and then we will be solving the simpler form for the quantum well. Okay. Is it clear? So, therefore, what will be the solution for, let us say this is 1. So, the region 0 to a and the region minus b to 0, let us say equation 2. So, therefore, solution to equation 1, that is in the region 0 to a, this is the quantum well solution. So, what do you get? We can write in terms of exponential functions. So, we have a e power right running wave I k x, very good, plus b power minus I k x, good. And therefore, if you look at solution to equation 2, this is the region beyond the potential barrier, potential constraint. Okay. So, the electrons if with energy is greater than u naught can basically escape the potential constraint and they can move about freely. Okay. So, in this particular case what is the solution? So, to equation number 2, yes, because we have put plus u naught minus e. Okay. So, therefore, we can write this as what? C e power, we should use a different wave number now, let us say q, okay, plus d e power minus q x. Okay. So, now how k and e are related to u to e. So, now k will be, or we can write e as h bar square k square by 2m, this is in the region 0 to a, and now in the region minus b to 0 your e will be, your u minus e will be h bar square q square by 2m u naught. Okay. So, this is the relation between your energy and your wave vectors k and q, right. We have already seen this yesterday when we looked at finite potential wells. Okay. So, now again you have 4 constants and you need what 4 conditions to solve. Now, we can apply the continuity of wave function and its derivative at x equal to 0. So, x equal to 0 is the point where you have transition between solution 1 and solution 2. So, you can call this psi 1 and psi 2 in fact if you want. Okay. So, therefore, at x equal to 0 you can apply psi 1 of x should be equal to psi 2 of x, and so are their derivatives. Have psi 1 prime should be equal to psi 2 prime. So, this gives you two equations for finding out two unknowns, but we have two more unknowns to be determined and we need therefore two more conditions. And what can we do? So, now we go to this periodicity. Since this unit cell is periodic, okay, so we try to somehow, we know the potential is periodic, okay, but how do we link the solution for a periodic potential? So, we use what is called as Bloch theorem. So, this gives you the form of the wave function that should be applied if your potential is periodic. Okay. So, this says that psi of x plus a plus b, that means if you are looking at the wave function at some position which is periodic with a plus b, the potential is periodic every a plus b. So, after a plus b at that particular position, this is linked to the wave function at x as this into e power I. Now, I am going to use kappa here. Okay, this is another wave vector, not to be confused with k and q. Okay. So, we will come to that, power multiplied by a plus b. So, this is your Bloch's theorem without going into the details of its derivation. So, this is for periodic potentials in a crystal. So, the periodicity in the wave function is expressed in this particular format. And what is kappa here? So, kappa is another kind of a wave number. This is for a crystal, however. So, what we have written as k and q, these are the wave numbers corresponding to the electrons. Okay. So, now this kappa is the wave number corresponding to the crystal, and this puts a condition again that it is not continuous, but it is discrete given like this, and n can be 0 plus or minus 1 plus or minus 2, 3 and so on. Okay. So, this is basically the kappa, and what is L? L is the length of the crystal. So, it can be expressed as capital N into a plus b, that means where n is the number of atoms. So, if we are if you are looking at this potential that we have written here, so it is periodic every a plus b. So, if you have n number of atoms, the entire crystal length will be n times a plus b. So, that is the length of the one dimensional crystal. Okay. So, within this crystal, this wave vector of the crystal will exhibit some kind of relationship. So, which is 2 pi n by L, where n can be 0 plus or minus 1 plus or minus 2 etc. Okay. So, if you therefore apply this Bloch theorem at x equal to a, that means we are going to write the wave function at x equal to a in terms of x equal to minus b, right. So, because it is periodic about a plus b. So, at x equal to a, we are going to apply Bloch's theorem, which says that psi of x should be x equal to a should be equal to psi of x equal to minus b times exponential I kappa A plus B, right. So, therefore, if you substitute our wave functions, you will be getting A e power I k A plus B e power minus I k A is equal to C e power minus q b plus D e power q plus q b times e power I kappa plus B. Okay. So, you have equation number 3. Okay. So, you had equation 1, these are the conditions, boundary conditions 2, now you have periodic condition 3, and what should be the fourth condition? Again the derivatives also should follow the same theorem. Okay. So, again you can apply this for psi prime at x equal to A should be equal to psi prime x equal to minus b times e power I kappa A plus B. Okay. So, this should give you, can you all find this out, write it down. So, what do you have? I k I k A minus b e power minus I k A is equal to q into minus c e power minus q b plus d e power q b times exponential I kappa A plus B. So, this is your condition number 4. Okay. So, therefore, I am not now going into further details, you can apply these 4 conditions and therefore, find out the constants, and I will only write down the final equation what comes out. So, we can express P by k A into sin k A plus cos k A is equal to cos kappa A. So, this is your final equation that you get to solve for q and k. Now, where p is nothing but q square into b times A by 2. Okay. So, I am just clubbing this wave vector q square times b times A. So, b is basically the width of that barrier, A is the width of the well, right, divided by 2. So, this p is what is written here. So, you have a final equation, okay, which you can solve for getting the wave vector k. So, now if you plot this, so how do we find the solution? By plotting we can get the roots of this equation. So, we can actually plot on the x axis capital K A by pi. So, this is some kind of non-dimensional wave number. Okay, I am non-dimensionalizing the wave number as K A by pi on the x axis, and I am plotting this entire function on the y axis. So, to find out the roots of this equation. Okay. So, therefore, on the y axis I have p by k a sin k a plus I have cos k a. So, if you plot this function, so k a by pi can actually take also negative values. So, you have 0, 1, 2, 4, and on this side you have minus 1, minus 2 and minus 4. Okay. So, you can draw so this will be looking like so about 0 it is symmetric, okay, and you have a peak at 0 and then it goes about like this. So, this is how this function will look. Okay. Now, if on the right hand side what do we have? Cos kappa a. Okay. So, what will be the maximum value, minimum and maximum for this function? Plus 1 and minus 1. Okay. So, therefore, if you plot plus 1 and minus 1, so this will be somewhere roughly 0, and you will have plus 1, you have minus 1. Okay. So, therefore, what is the region in which you can find the roots? Only where they coincide, okay, where values of cos kappa a will be equal to these values. Now, there are values which are above plus 1 and minus 1 for this particular function, that is, if you shade it, these are regions like this. Okay. Now, these regions are not possible because they are exceeding the right hand side values. So, these are therefore called forbidden regions. Okay. So, you cannot have physical values of this function because they do not lie within this right hand side cos kappa a. So, therefore, they are not included in the final solution. Okay. So, this is the region where no electrons can exist. Because they are not satisfying, let us say this is equation number 5. Okay. Since they do not satisfy, So, now what we can do is if therefore, you want to calculate the energy of the electrons. So, what do we do? So, we have to simply put vertical lines, okay, and then that would be giving the corresponding value of k, which in turn determines what is the energy. So, that energy is calculated using these relations, right. So, all you need to do is only look at the corresponding roots of k, the wave vector or wave number k, and that will give you the energy of the electron. So, therefore, if you draw a vertical line like this, okay, so you can therefore find out the corresponding value of k for this, and which can be translated into energy. So, similarly, all these different lines. Now, when it comes to this forbidden region, so there no electrons can exist, therefore, you cannot have any values of energy there. So, now what happens from here to here, you will produce a band gap, you understand. So, this is how in semiconductors, metals, we talk about the concept of band gap between two bands, so valence band and conduction band. So, how this band gap comes is because of this forbidden region. So, when we now convert this, and you should also understand that what I have drawn here are not perfectly continuous, cannot be continuous lines as well, okay, because the values of cos kappa a, these are discrete because of the fact that k is kappa is discrete, right. Kappa is discrete because it is 2 pi n by l. So, therefore, if you look at this here, so you will have discreteness, you will have this, you will have this like this. So, these are discrete solutions, okay, and wherever this point intersects here will be one value of k, you understand, okay, and where this cuts here will be another value of k. So, these are actually again discrete solutions. So, what we talk about solutions of k are themselves discrete values, not continuous, they are, you can say, quasi continuous. On top of that, you have this forbidden region which is quite discontinuous. So, this will result in the band gap or separation between the energy bands. So, therefore, we can now convert this plot into a plot of energy versus kappa, okay, that is called the dispersion curve. So, people sometimes use kappa, in some textbooks it is just written as small k to distinguish it from k and capital K and Q. The capital K and Q are the wave vectors for the electrons, the kappa or the small k is used to determine, is used to denote the wave vector for the crystal, okay, which is 2 pi n by l, right. So, we can actually convert now this plot into a diagram for the energy bands. So, where I plot the energy E by E naught, non-dimensionalizing the energy. So, where E naught is nothing but h bar square by 8 m a square, this is some non-dimensional number. Similarly, I can now non-dimensionalize the crystal wave vector, which will be kappa by pi by a, kappa a by pi, like the way I plotted here k a by pi, okay, this is for the electron energy. Now, this is for the crystal. So, this is your crystal wave number, okay. So, just to make sure you do not get confused, this is your electron wave number. And then what do you find is for a given value of energy, you can have multiple values of these wave vectors, okay. So, therefore, you can draw something like and once again you can mark the origin for this 0, and then you can have similar to this 1, 2, 3, 4 and so on. Similarly, you can have -1, -2, -3 and so on. Okay. So, that means you for a given value of energy you can say this value of energy E1 by E0, you have multiple values of the crystal wave number. Okay. So, how do you understand like that? How do you understand that? So, that crystal wave number values are basically these discrete lines. Okay. So, you draw a vertical. So, that is one given energy, value of energy. So, one given value of energy can take multiple values of this kappa A. Okay. And now, we are converting that plot into an energy versus crystal wave vector plot. So, this plot is called the dispersion plot, very important for solids. So, finally, what it means is we are not interested in not only the individual energy diagram of the electrons, but for the entire crystal, how this energy is dispersed. Okay. So, this is called the dispersion plot, or capital E versus, people use either small k or kappa. This is the crystal wave number. So, and now if you plot the next energy level, for example. So, now you will have this energy gap, band gap coming into picture. So, wherever you have this band gap, you will have a big space. Okay. So, therefore, you can plot the next set of, so this is basically your band gap, okay, coming from the forbidden region. So, you miss all the values in the forbidden region, you do not plot them, and this creates the band gap. And similarly, you can continue this. So, this is all periodic. So on and so forth. Okay. So, now once again you see that these are all periodic, because we are talking about crystals here. We have applied a periodic potential, we applied periodicity of wave function through Bloch theorem. So, therefore, the solution is periodic, the values of the dispersion plot are also periodic. So, we will only take one unit cell again. Okay. So, that unit cell is now extending for k a by or kappa a by pi between -1 to +1. So, that is the unit cell about which the dispersion curve is also periodic, and if you just plot only for that region. So, we are talking about -1, 0, 1. So, we have kappa a by pi, and we are plotting E by E naught. So, I will just the box. So, the lowest value will be something like this, symmetric about 0, and then you will have something like this, then you have a band gap, and then you will have something like this, and again you have a band gap, and then something like this. Okay. These are the different energy levels. Okay. Now, also these are actually not perfectly continuous, as I said, you have little bit of discontinuity. So, if you really want to plot them, it will be like this, because your kappa a is also a discrete value. Okay. So, really speaking, these are quasi continuous. but nevertheless you can assume them to be some solid line like this. Okay. So, you understand. So, this is how for a real structure the electron energy levels look. We started from calculating the electron energy levels in a quantum well, and now we have gone to a real structure, and we have seen how the dispersion of energy levels take place in a crystal by applying so many conditions. Okay. And finally, also this discreteness results in a forbidden region which causes these band gaps to appear. So, now what does this, how does this influence the filling of electrons, okay, and how this can be used to classify materials. So, this is what we will quickly do now in the last 10 minutes. So, now if you see, look at the periodicity of this dispersion curve between -1 to 1. So, it is symmetric about 0. Therefore, even if you depict for 1/2 maybe from 0 to 1, so that should be simply a mirror of the other side. So, therefore, in order to classify materials, I will just give an example of how these energy levels are filled for different materials, and that is how they are actually classified. So, if you, for example, first, so I am only drawing the positive quadrant. So, you have kappa A by pi from 0 to 1, and you have E by E naught on the vertical axis. So, this will be looking like this will be looking like this, and this will be looking like this. Okay. So, I have just drawn 1, 2, 3 for 0 to 1. So, first if you take the case of metals, so if you take the case of metals, what do you find? The electrons are filling all the lower energy levels. From the lower energy levels it keeps going. Now, you have a band gap, but the electrons do not have a problem in metals. Okay. So, at 0 Kelvin, if you look at till what level they are filled, so this is called the Fermi level. Okay. So, Fermi level tells you what is the maximum energy to which the electrons are filling the energy levels at 0 Kelvin. Okay. So, you will see that in metals already some electrons have occupied the second energy level, energy state, and the rest is all vacant. That means, now if you keep increasing the temperature, these electrons can freely move within this particular band without any problem, and therefore, all these are what? Conduction electrons or free electrons. So, in that case this becomes the conduction band. So, you have to therefore look at the Fermi level, and from then onwards you will decide what is the valence band, what is the conduction band. So, in this case conduction band, you have plenty of space to move the free electrons. So, therefore, these are behaving like metals, they are very good conductors of heat and current. Okay. So, if you then go to the case of an insulator, so you can draw another one. E by E naught kappa A by pi. So, now we are going to describe how these states are filled. So, in the case of insulator, what do you think will probably happen? it is not that it should be only filled till here, it can also occupy this energy level at 0 Kelvin. Okay. So, then this could be the Fermi level at 0 Kelvin. Now, this will be the position for the case of insulator. Now, what happens? You have a band gap E subscript G, a band gap in the energy separation. So, at 0 Kelvin this is your condition. So, therefore, at higher temperature, but the problem is this band gap is too much in insulators. In semiconductors this can jump. Okay. So, therefore, then this becomes your conduction band, and this is Fermi level, end of Fermi level now will become this band will be the valence band. That means, the valence band is completely filled and conduction band is totally empty, devoid of any electrons. So, therefore, there are no free electrons. So, this band gap is too much. Now, we are saying that band gap looks maybe looking small, but I have probably drawn this for a semiconductor here, but if you are looking at a real insulator, the actual conduction band can start from somewhere here. So, then this could become your band gap. Okay. So, therefore, the typical thumb rule, if your band gap is greater than 3 electron volts, okay, between the valence and conduction band. So, this will result in material becoming an insulator. If it is less than 3 electron volts, so this will be a semiconductor. In fact, the energy at room temperature kBT, if you calculate in electron volts, this will be 0.026 electron volts. So, that means, if this has to be a semiconductor at room temperature, the band gap should be of this order for the electron to overcome this band gap. Okay. Otherwise, it will be a semiconductor at a higher temperature. Okay. So, we talk about room temperature semiconductors. So, that means that their band gaps are of the order of this size of this electron volts. So, again in semiconductors you have different classifications, you have intrinsic type and you have extrinsic type. So, all these are now going into electrical engineering, but I am still because you should at least understand how they look, beyond that we are not interested. So, in the case of intrinsic is what we are talking about, a band gap which is comparable to the kBT, whatever temperature you are talking about. So, then they can naturally transition by themselves, but if they need an external help, okay, so they become extrinsic semiconductors. And how that will work? So, that means you take a donor or acceptor whose Fermi levels can be tuned to be either close to the valence band of this basic material or to the conduction band. So, accordingly it can become an N type or a P type semiconductor. Okay. So, probably you have heard about this kind of explanation when you are talking about semiconductors, but not in terms of the different energy levels and energy gaps. Okay. So, if you look at therefore the N type semiconductor, okay, so this is all filled. Now, what could happen is this band gap may be okay to move at certain temperature. So, 2 electrons may be jumping from here to here, and therefore, 2 holes are created on the valence band. On the conduction band you have 2 electrons, and now you introduce a donor. So, the Fermi energy of the donor is basically closer to the conduction band of this material. So, therefore, at higher temperatures what will happen, there is chance of these electrons from the donor jumping to the conduction band of the acceptor material, right. So, these electrons do not have enough energy. So, they cannot simply jump from here to here, but the donor electrons can do, because their Fermi levels are closer to the conduction band. So, therefore, this will result in the creation of what is called as N type semiconductors. Okay. So, the donor, what do you remember, what is the standard? Phosphor. Okay. And what happens when you want to make a p type semiconductor? You want to have an acceptor, okay, whose Fermi level will be closer to the valence band of this. Okay. So, in this case you call this as acceptor, and the commonly used semiconductor is boron. So, what happens is, from the semiconductor material these electrons can jump to the acceptor energy levels. Okay, they cannot jump to their own conduction band, but to the, and therefore, what happens is excessive empty spaces or holes are created, right. So, when these go, so in the base material you have therefore holes. So, therefore, this become p type semiconductor. Okay. So, I mean, to give you therefore a kind of overview, so depending on the way the energy levels are filled, and depending on this forbidden region gap, so this will decide what is the kind of material it will be, whether it is a metal or insulator or semiconductor. Okay. So, this basic understanding is required for you, because when you are distinguishing the materials and when you now start looking at calculating all the macro scale or micro scale properties, you have to be sensitive to what kind of material you are doing this. Okay. So, we will stop here, and from the next class we will focus mainly on these dispersion curves. We will do away with the quantum mechanics, because the quantum mechanics in the solid state physics is learnt only till this point, where you know how to produce these dispersion curves, and after the dispersion curves are obtained, we will continue with that. We will make approximation to the way the dispersion curves look. What I have drawn here, this could be the actual dispersion curve, but we will make approximations like parabolic approximation and use those parabolic approximations, okay, into calculating what is called as density of states. Okay. So, we will do that in the next week. Okay. Thank you.